Hi everyone and welcome back. So this is our next topic in our discussion of energy for Unit 3, and we're going to be looking at exothermic and endothermic reactions. This relates to Chapter 2 of your textbook, and let's get started. The key things that VCAA wants us to concentrate on in this case is being able to compare exothermic and endothermic reactions, including their enthalpy changes, combustion of fuels as exothermic reactions with reference to joules as the SI unit, including enthalpy change as kilojoules per mole, be able to convert these between joules, kilojoules, and megajoules, again, metric conversions coming up, be able to write thermochemical equations, and also be able to determine these values experimentally using specific heat capacity calculations and Q equals MC delta T, which we did previously in Unit 1 and 2. Okay, so the first of our videos is just going to concentrate on these first two dot points here, referring to endothermic and exothermic reactions, defining those and talking about them in terms of energy. So as we will recall from Year 10, all chemical reactions require there to be a collision between particles that has the correct orientation and energy greater than the activation energy. This essentially means that when particles collide, they undergo a change, the bonds and the reactants are broken, and new bonds are formed in the products. There are many different types of reactions, and we have seen a large number of them so far in terms of addition reactions, redox reactions, acid-base reactions. All of these reactions, however, have these requirements. The collisions do not always result in a change or a chemical reaction occurring because they may not have sufficient energy, or in the case of some reactions, they may need enough energy to get them started. This is generally the case with combustion reactions. If you think about it, fuels do not tend to spontaneously combust when they're sitting around. Wood will stay unburning until it is ignited. Same goes for liquid petroleum or petroleum fuel. It has access to oxygen inside the fuel tank, but our cars don't spontaneously combust, and this is because we must give them ignition or a spark source to get that reaction to go. So when we're talking about chemical energy, and we started talking about chemical energy and energy transformations, we're talking about a substance's chemical energy that is stored in the bonds and the activity of the atoms within those molecules. This is essentially the chemical potential energy, or the chemical energy of a substance, is equal to the potential energy within the bonds and the kinetic energy within the molecules itself. Chemical potential energy results from a number of different things. This is the repulsion between protons in the nucleus, the repulsion between electrons in the same shells or in the electron cloud around the nucleus, the electrostatic attraction between the electrons and the protons, as well as the kinetic energy in the bonds themselves, bending and stretching. So while there are multiple ways that energy is expressed within a molecule or atom, all of these added together give us the chemical potential energy that we're referring to as the energy stored within a particular molecule. When we talk about energy, it is important for us to define the difference between the system and the surroundings, because when we're talking about energy, we're often talking about energy flow from one to the other, particularly when we're talking about chemical reactions occurring. So if we consider this flask where a chemical reaction is occurring, it could be a neutralization reaction, so say HCl plus sodium hydroxide reacting to form NaCl and water. This is going to be an exothermic reaction. It's a neutralization reaction. It will give energy off to the surroundings. So the reaction flask would increase in temperature as it occurred. When we refer to the system in chemistry, we are referring to the chemical reaction itself. Okay? So the chemical reaction is the system. Okay, the surroundings is everything else. This includes the solvent, so this would be done in an aqueous environment, which means that the water this reaction is dissolved into would be considered the surroundings, as would the flask, the air, everything else is the surroundings. So if this reaction, which it is, was exothermic, the surroundings would increase in temperature. So the solution itself would increase in temperature, pass that on to the flask and the air surrounding it. But it would all be coming from the system, which is the chemical reaction itself, because the energy is being released from the chemical potential energy within those compounds. With chemical reactions, the energy is stored within the bonds of the compounds. When a reaction occurs, the bonds of the reactants are broken, and this requires energy, so bond breaking is always an energy requiring process, and then bond making gives energy back. We're talking about whether or not the temperature of the system increases or decreases is always a matter of, did it take more energy to break the bonds than we got back? Or did we get more back than what it took to break the bonds? That's what we're talking about when we're trying to define the energy changes within the systems that we're looking at. Most of the reactions that we know produce energy: combustion engines, Bunsen burners, fuel for rockets, and these kinds of things. When we think about chemical reactions, we do tend to think of reactions that produce energy, specifically when we're talking about fuels. One of the other types of energy that can be given off is light, and we see that with chemical glow sticks, where these are an endothermic reaction, where the energy being given off is being given off as photons of light. So these energy producing reactions, can typically produce light and heat. Sometimes there may also be sound, and these types of energy can be harnessed through energy transformations to produce other types of energy. So when the reaction produces energy, we refer to it as an exothermic reaction. Exo, I like to think of exo and exit. So this is where energy is exiting the system. So it goes from the system to the surroundings. It is pushing out energy. Whereas when we have a reaction that gets colder or absorbs energy, that is where energy from the surroundings goes into the system. And we refer to that as an endothermic reaction. And this is the type of reaction that we see in chemical ice packs. So in exothermic reactions, we have energy coming out into the surroundings. Endothermic reactions, the energy moves in. And this is to the system. And this is critical when we start to look at these in more detail. With a change of state, we need to realize here that these are also endothermic and exothermic situations. With a gas, we have a high energy state. In a solid, it is a low energy state. If we think about these in terms of kinetic energy, our particles are only vibrating and in place in a solid, whereas a gas has a large amount of movement and kinetic energy in the system. So, of course, liquids sit in between this with a medium level of energy. And you'll remember from year 11 where we talked about latent heat of vaporization and latent heat of fusion, it took a lot more energy to go from a liquid to a gas, requiring as we go to a much higher energy state. So the energy absorbed by the system to turn into a gas is much greater. And we see that when we look at things like our latent heat of vaporization and latent heat of fusion in these equations here. These are actually the reverse, so going from a liquid to a solid, so from a higher energy state to a lower energy state, it is producing energy. And same with a gas to a liquid. It would produce that much or give off that much energy in order to go back to the lower state. So if we go from low energy to high energy, energy needs to be absorbed. When we go from high energy to low energy, energy is spat out from the system. This change in energy is what we refer to as a change in enthalpy. So when we talk about chemical energy, we are talking about enthalpy. These terms are fairly interchangeable, but we will start to use enthalpy in all our written responses. So the chemical energy of a particular compound is its potential energy plus its kinetic energy, and this is known as the heat content or heat of reaction, which is given the symbol capital H. So capital H is equal to enthalpy. So when we talk about enthalpy, it is impossible for us to stick a probe into a molecule and directly measure the exact amount of enthalpy or energy that it contains. Okay, so we can't do this for reactants or products, but we can measure the change in enthalpy when a reaction occurs by measuring the change in temperature. Change is given the symbol capital delta from the Greek alphabet. So when we talk about delta H, we are talking about the change of enthalpy, okay, and it is given the unit kilojoules per mole. Okay, so important to make a note of this. We need to make sure that when we're talking about the energy being produced or absorbed, it's in kilojoules, and when we talk about enthalpy, it's going to be kilojoules per mole of substance. So when we measure enthalpy, okay, this is when a chemical reaction is occurring. We can measure the change in the systems, and we do this by measuring a change in temperature. Okay, measuring the energy absorbed or released by a system can be done by measuring the change in temperature of the surroundings. Okay, because energy coming into or out of the surroundings will cause a direct change in temperature. When we're talking about exothermic reactions, these are reactions that the energy exits from the system into the surroundings. This is because the enthalpy of the products is less than that of the reactants. So a reaction will lose energy primarily as heat to its surroundings. An exothermic reaction will cause the temperature of the surroundings to increase because that difference in energy is released into the surroundings. And all combustion reactions are exothermic by definition. They give us heat and light that is being released on the conversion of the reactants to the products. Other reactions that are exothermic are also neutralization reactions. You may remember looking at enthalpy level diagrams back in year 10, but not knowing what the enthalpy stood for. So we often put energy up on our y-axis, and we're actually talking about enthalpy, and then reaction progress across the x-axis. For an exothermic reaction, you remember we had a line up here, and then it went this way. And this was the profile for an exothermic reaction. And this is because the reactants have much higher energy than the product. The excess energy is given off to the surroundings. So here we are here, where we have energy exiting from our system to our surroundings, with our reactant starting at a higher energy level, our product being a lower enthalpy level, and the difference being a negative delta H. So it's a negative delta H value for an exothermic reaction. Okay, and we can see here, this is the reaction for methane to produce CO2 and H2O. When we're sketching these enthalpy level diagrams, it is important that if you know what the reactants and the products are, they are listed on your diagram in the appropriate place. For an endothermic reaction, the enthalpy of the products is more than that of the reactants. Okay, so the bonds within the products have actually absorbed energy from the surroundings. Okay, so this is an endothermic reaction because energy is being absorbed from the surroundings. The temperature of the surroundings decreases, so it gets colder. Decomposition of calcium carbonate is an example of one of these reactions. So in this situation, if we're looking at it graphically, the energy is coming from outside into the system. So this means that it will cool the surroundings. For a reaction mixture done in aqueous solution, this means that the solution will go down in temperature while the reaction occurring in that solution goes ahead. So if we look at the calcium carbonate going through to calcium solid and calcium gas, this will absorb energy from the surroundings in order to get to the higher energy products from the lower energy reactants. So if we look at this, when we have a question, we're essentially going to be thinking about the energy of the system and the surroundings to answer this. So which statement below is correct for an endothermic reaction? Remembering endothermic is going to be absorbing energy from the surroundings. Okay, so and a higher energy is generally a less stable bond. Okay, so if it has a lower energy, the bonds are stronger, they're more stable. So in this case, the bonds in the reactants are stronger than the bonds in the product. So we're thinking of an endothermic. This is a possibility. The bonds in the products are stronger than those in the reactants. No, because they will be more energetic. The enthalpy of the products is less than that of the reactants. No, because we're ending up with the products being higher. Heat energy is given out to the surroundings. No, because endo heat energy is brought in. So that confirms that A is our correct choice. Okay, so when we're talking about enthalpy, we talk about the overall change in enthalpy, delta H. This is calculated by taking the enthalpy of the products. It is the difference between the products and the reactants. So it is the enthalpy of the products minus the enthalpy of the reactants. So for an exothermic reaction, we said that the product was less than the reactants. So we would end up with a negative value because this is going to be the smaller number minus a larger number. So it will always be negative for an exothermic reaction. For an endothermic reaction, the energy of the products is higher than the energy of the reactants. So now this difference will give us a positive value, and delta H will always be positive for an endothermic reaction. So summarizing what we have learnt, we know that for when we're talking about the systems and the surroundings, for an endothermic reaction, delta H will be greater than 0. It will be positive because the enthalpy of the product is greater than that of the reactions, and the heat energy will flow from the surroundings to the system. For an exothermic reaction, the energy is going to flow from the system to the surroundings, increasing the temperature of the surroundings. Delta H will be less than 0 because the enthalpy of the products will be less than the enthalpy of the reactants, for the overall change being given enthalpy of the products minus enthalpy of the reactants. And this is our summary in dot points here for you to ensure that your notes cover each of these points. And I'll see you in class for some practice questions.